What if you could shrink to the size of an ant? From The Incredible Shrinking Man to Ant-Man, Hollywood paints a picture of amazing adventures. But let's imagine this for a second in reality. You open your eyes in the grass, and the first thing that kills you is the air. It burns your lungs like pure poison. You try to take a step, but your bones fracture under the weight of your own head. A dewdrop falls nearby, and for you, it's not water, but a sticky, viscous prison. It feels less like a liquid and more like a giant ball of jelly that completely engulfs you. Why is a popular superpower, in reality, the fastest and most agonizing way to die? The problem isn't that the laws of physics change. They remain constant. What changes is their influence. Forces that seem insignificant in our world, like the surface tension of water, become dominant in the microworld, and the force that governs our lives, gravity, is barely felt there. To understand why our world and the insect world are two different universes, we need to get acquainted with the main tyrant of small scales. This villain is called the square cube law. It was first formulated by Galileo Galilei. It states that as an object's size changes, its surface area changes by the square, while its volume changes by the cube. Galileo described this principle in his 1638 work, Discourses and Mathematical Demonstrations Relating to Two New Sciences, pondering why the bones of giant animals must be disproportionately thicker. This simple mathematical ratio is the root cause of why giant ants from horror films cannot exist, and a shrunken human is doomed. This law dictates everything from bone strength to body temperature, and it is absolutely merciless. Let's apply this law in practice to our own bodies. The strength of a bone or muscle depends on the area of its cross-section, a square. The weight it must support depends on the body's volume, a cube. When you shrink, your weight decreases much faster than your strength. This is why a leafcutter ant can carry a load 50 times its own weight. It has colossal relative strength. But for a shrunken human, the opposite is true. Your bones, designed for a large body, would become catastrophically fragile. Like dry spaghetti, you would turn into a brittle glass figurine that shatters with the first attempt at movement. Here's another problem: heat. Our body constantly generates heat through its volume and releases it into the environment through the surface of the skin. Shrink to the size of an ant, and your volume, your internal furnace, will shrink thousands of times more than your skin's surface area, your radiator. You would lose heat at a catastrophic rate. Even on a hot summer day, you would freeze to death in minutes. To survive, you would have to, like a shrew whose pulse reaches 1,000 beats per minute, eat several times your body weight daily just to stay warm. Instant and inevitable hypothermia. This same law explains why water striders glide across water. The pressure they exert on the surface is so small that surface tension holds them up. A shrunken human would still be too dense and heavy to perform this trick. We would fall into the water and be trapped. The square cube law puts us in the worst of both worlds. Too fragile, yet too heavy. And it works both ways. Enlarge an ant to the size of a bus, and its mass, its cube, would grow so much that its thin legs, its square, would simply buckle. Its respiratory system, designed for diffusion, would be unable to deliver oxygen deep into a massive body, and it would suffocate. The only reason giant dragonflies like the Meganeura, with a wingspan of 75 centimeters, could exist in the Carboniferous period, about 300 million years ago, was oxygen. Its concentration in the atmosphere reached 35% instead of the current 21, allowing their respiratory system to function on a larger scale. The square cube law is a universal size limiter for any biological species, but this law is only the first of the problems. It describes how your body breaks down. It doesn't tell you how the world itself turns into a weapon. Recall the dewdrop. For us, surface tension is a force that merely gives it shape. For a creature of your new size, it's an insurmountable elastic film. If you touch it, you won't break free. The cohesive forces of water molecules would be stronger than all your muscles combined. Gravity pulling you down would be hundreds of times weaker than this molecular grip. You would find yourself in a sticky cocoon that slowly drowns you. Any summer rain would turn into a carpet bombing of such watery traps. The air, which we barely notice, would also become an enemy. Its viscosity becomes enormous for a tiny object. Every step you take, every swing of your arm, would meet such resistance as if you were trying to wade through the bottom of a pool filled with thick syrup. Physicists describe this as a world where inertia is almost meaningless and viscosity rules everything. For a microbe, swimming in water is like a human swimming in asphalt, and you would find yourself in this nightmare. The rapid jumps of a grasshopper or the flight of a wasp require entirely different biomechanics and incredible energy expenditure. We, however, would simply slowly and clumsily flounder in this viscous ocean, but the greatest irony awaits you within. Our lungs have a huge surface area, perfectly tuned for gas exchange at 21% oxygen in the atmosphere. If you reduce your body but maintain this efficiency, you will get a lethal overdose. Oxygen in such a relative concentration would become a poison. It would begin to oxidize and destroy the tissues of your lungs and blood. This condition is called hyperoxia. Deep sea divers sometimes encounter it when using incorrect gas mixtures. Each breath, instead of giving life, would burn you from the inside out, and even if you somehow survive, you would be blind and deaf. Our eardrums are too large and inert to pick up the high frequency vibrations that insects use to communicate. Their world would be almost silent to us. Our eyes would encounter the physical limit of light diffraction. Your tiny pupils simply wouldn't be able to gather enough photons to form a clear image. You would see only blurry patches of light and shadow in a world that is actually filled with minute details. At this level, another invisible force comes into play: Brownian motion. These are the chaotic jolts of the air molecules themselves. We don't feel them, but for an object a few millimeters in size, it would be like a continuous vibration, like a jackhammer. It was by observing this phenomenon in 1905 that Albert Einstein mathematically proved the existence of atoms. For you, this great scientific discovery would become physical torture. It would knock you off your feet, prevent you from focusing, and make any precise movements impossible. The air itself would become a force hitting you from all sides. And finally, static electricity. For us, it's a funny little shock. In the microworld, it's a powerful adhesive. Accumulating a small charge, you would stick irrevocably to the first leaf or dust particle. You simply wouldn't have enough strength to overcome the intermolecular forces of attraction, the same ones that allow a gecko to run across the ceiling. For it, it's an adaptation. For you, another trap in a world where every grain of sand is a boulder and every drop of water is an ocean. But all these external threats pale in comparison to what would begin to happen inside your body. The fastest and most inevitable collapse would occur in your circulatory system. Blood is not just a red liquid, it is a suspension consisting of billions of cells. Under normal conditions, they flow freely even through the thinnest capillaries. But if you shrink, your capillaries would become thinner than the red blood cells themselves. The diameter of an erythrocyte, a red blood cell, is about 8 micrometers. It cannot change. This is like trying to push a basketball through a garden hose. Throughout your body, in every organ, thousands of microclots would instantly form. Your heart, a powerful pump, would encounter insurmountable resistance and simply would not be able to push this thickened sludge. This is not a slow death. It is the failure of the entire circulatory system in the very first second. Even if blood miraculously continued to flow, your brain would fail you, or more precisely, its operating speed. The speed of nerve impulse transmission along an axon is a physical constant, reaching 120 meters per second. In our large body, this ensures almost instantaneous reaction, but in the microworld, where predators like spiders move with lightning speed, this delay becomes fatal. By the time the signal from your eyes reaches your brain, and the command from your brain reaches your muscles, a critically long time will have passed. You would exist with a constant delay, as if playing a computer game with a terrible internet connection while all other players are nearby. You simply wouldn't be able to react to any threat, and a threat would also come from your own metabolism. As we recall, to avoid freezing to death, you would have to eat almost continuously, consuming several times your body weight in food daily. But your digestive system is designed for slow and efficient calorie extraction. It wouldn't be able to process such a flow. A monstrous paradox would arise. You would die of starvation with a full stomach. Your body simply wouldn't be able to assimilate energy quickly enough. You would burn out from exhaustion, even if you were constantly chewing something. However, all this pales before the fundamental problem of cellular structure. There are only two options here, and both lead to a dead end. If your cells also shrink when you do, their internal structure, mitochondria, nucleus, ribosomes, would become so tiny that the basic laws of chemistry and biophysics would simply stop working within them. There is a concept of a minimal viable cell, and you would go beyond that limit. If your cells remain the same size, then your ant-sized body would consist of only a few thousand cells. This is catastrophically few. It's impossible to assemble a complex brain, a liver, or even proper skin from them. You would simply cease to be a complex organism. And finally, your immune system, your leukocytes, your defender cells also have their size. A macrophage, a devourer of bacteria, reaches 20 micrometers. In a world where you yourself are insect-sized, an ordinary amoeba or paramecium would become giant monsters to you. An amoeba can grow up to 500 micrometers. That's like one police officer trying to arrest an entire building. Your leukocyte would physically be unable to engulf such an enemy. Any simple infection would become an insurmountable force for your body, and you yourself would turn into an ideal breeding ground for the microworld. Your body, designed for dominance in the macroworld, turns out to be completely defenseless at the micro level. It doesn't just break down, it turns against itself. Evolution solved the problem of poisonous air and clogged vessels with one ingenious move. It simply removed the lungs. Instead, an insect's body is permeated by a network of tiny tubes, tracheae, which deliver oxygen directly to every cell. This is similar to a ventilation system in a huge building, where air ducts lead to each individual room. Such passive diffusion works perfectly at small scales and does not require a complex circulatory system for oxygen transport, solving two of our deadly problems at once. An internal skeleton like ours is also inefficient at a small scale. That's why evolution gave insects an exoskeleton. This external chitinous armor provides phenomenal strength at low weight, bypassing the trap of the square cube law. Chitin, a strong and lightweight polymer, is similar to modern composite materials. Essentially, insects wear their high-tech armor on the outside. It also protects them from dehydration and small predators. But most importantly, insects do not fight the physics of the microworld. They use it. Their bodies are covered with waxy cuticles that repel water, turning a deadly trap into a mere inconvenience. Special hairs on their legs allow them to walk on water using surface tension as a reliable support. They do not violate the laws of physics, but masterfully exploit their peculiarities. They have turned physics, deadly for us, into their main evolutionary advantage. The conclusion is obvious. Life on a small scale is not just a miniature copy of ours. It is an entirely different engineering and biological paradigm, as biologist J.B.S. Haldane wrote in his famous essay on being the right size. For a mouse and any smaller animal, gravity practically presents no dangers. Insects are not small animals, but highly specialized organisms, perfectly adapted to a set of physical laws that would be a death sentence for us. So what would kill you first? The square cube law. In the very first second, you would either freeze to death due to catastrophic heat loss, or your bones would break under the weight of your own head. You would be unable to stand, move, or maintain your body temperature. This is not an attack by an external enemy. It is a fundamental incompatibility of your design with the laws of reality at this scale. It is a physical knockout. If you miraculously survive that first moment, the environment would finish you off. The air would become a viscous prison for movement and a poison for your lungs. The first drop of water would turn into an insurmountable sticky trap. The world hasn't changed one bit, but you have become an alien object to it. You would be blind, deaf, and helpless in a world where every physical constant works against you. But even in a perfect safe container, your body would destroy itself. Blood would clot in your vessels, your heart would stop, and your brain would be too slow to comprehend what's happening. Your biology, a marvel of evolutionary engineering on one scale, transforms into an inescapable self-destruct program on another. It would become your last and most effective executioner. And here, the fantasy of a shrinking human reveals not its inconsistency, but a profound truth about ourselves. Our size is not an accident, but a fundamental condition of our existence. We are complex, intelligent, and alive precisely because our scale allows gravity to dominate surface tension and our biology to work effectively. Our size is a necessary condition for our consciousness. We are beings perfectly fitted to our tiny niche in the universe of sizes, and this is not a limitation, but our greatest privilege.